Today we are performing the experiment to find the focal length of convex lens. Now apparatus required in this experiment: convex lens, the stand to hold it, the object pin, here we will use red pin as object pin, the image pin, white one we will use as image pin, and a scale with length 100 centimeter. In this experiment, we measure the distance of object pin or image pin from the surface of the lens as you see. But actually we have to measure the distance from the optical center of the lens to pin. Optical center, that is the midpoint of these two surfaces. So we have to find the index correction for this given lens. Now to find the index correction, we have to find the thickness of the lens. So for that, place pin at any distance from the lens and first measure the distance between the center of the lens and pin as you see. Now hold another scale tangential to the lens on the back side at the geometric center of the lens as you see, and then measure the distance between this scale and pin. Now the difference of these two measurements will give you the thickness of the lens. In our case, the thickness of the lens comes to 1 centimeter. Now half of the thickness of the lens, that is the index correction. So in our case, that is 1 by 2 equal to 0.5 centimeter. Now first we have to find the approximate focal length of the convex lens. In theory, we studied this thing. The distant rays, means the rays which are parallel, incident on the lens, then will be focused at the focal point. So we will use that concept to measure the approximate focal length. And for that, first focus the distant object on the white paper. Now hold the white paper behind the lens as you see, and now you can see on the paper there is the faded image of the distant object. Now move your paper and obtain the sharp image of that distant object on the paper as you see here. Then measure the distance between lens and paper. It will give you the approximate focal length of the lens. Now in our experiment, the approximate focal length of the convex lens, that comes to 21 centimeter. Now place the object pin at a distance slight less than 2f from the optical center of the lens. Means here we have to place the pin slight less distance than the 42 centimeter. Now see the image of the object pin through the lens, and on the opposite side of the object pin place the image pin. Here it is a white pin. Image of the object pin that you observe is the inverted one. Now move your eyes left to right on the lens and observe this thing. The image pin and the image of the object pin are slightly detached from each other. Now we have to fix the position of image pin such that the parallax is removed between these two. It implies that both should move together. Now see, the parallax is removed here the image of the object pin and the image pin both move together when we move our eye throughout the lens. Now measure the distance of image pin from the center of the lens as you see. Now repeat the experiment for 5 more different positions of object pin between F and 2F, and for each position find out the image distance. Now here take the position of the lens, that is 0. Now with respect to that, the object pin is placed at 38 centimeter and its image is obtained at 41 centimeter on other side of the object. Now always we take the object distance that is negative, so here we have to write minus 38, and image distance that is on the other side, so it is positive. Now in our case, the thickness of the lens, that is 1 centimeter, so half of the thickness, that is the index correction, so add it in the observation. So resultant object distance comes to minus 38.5 centimeter and the image distance comes to 41.5 centimeter. Now we have equation to calculate the focal length of the lens, that is 1 upon f equal to 1 upon v minus 1 upon u. So resultantly we will get f equal to uv upon u minus v. But if we take the value magnitude wise, then we can write f equal to uv upon u plus v also, right? So substitute the values magnitude wise here, u that is 38.5, v that is 41.5, and solve this one. Our answer comes to 19.97 centimeter. Then similarly take 5 more observations for different object distances, and for each one prepare the observation table and calculate focal length of the lens. Then using this equation of the mean focal length, calculate the mean focal length. Now using the equation delta f equal to f square into delta u upon u square plus delta v upon v square, calculate error for each observation. It implies that suppose we take first observation, then delta f1 that is equal to f1 square into delta u upon u1 square plus delta v upon v1 square. Here take delta u and delta v, that is 0.1 centimeter, because we use the scale to measure the object and image distance, for which the least count, that is 0.1 centimeter. So possible error, that is 0.1 centimeter. And in this way calculate delta f1, delta f2, delta f3 up to delta f6, and then find the maximum possible error from these 6. Then after draw the graph of v versus u, take u on negative x-axis and your graph will be curved one as shown in this figure. Then from the origin in the direction 45 degree with respect to negative x-axis, draw a line as you see here. Then the point where this line intersect to the graph, draw normals on x-axis and y-axis. So on y-axis you will get the distance OA, and on x-axis you will get the distance OB, and write down these distances here in the observations. And then after using the formula f equal to OA plus OB by 4, calculate the focal length from the graph. Now here in table we have prepared the columns for 1 upon u and 1 upon v. So using these values of 1 upon u and 1 upon v, draw the graph of 1 upon v versus 1 upon u. 1 upon u that you have to take on negative x-axis. Your graph will be a straight line which intersect y-axis at a dash and x-axis at b dash. Now o a dash that is intercept on y-axis, write down it here in observation, and ob dash that is intercept on x-axis, write down it here in the observation. Then after using the formula f equal to 2 upon OA dash plus OB dash, calculate the mean focal length of the lens. Then represent your final result as f plus or minus delta f, which one is from calculations, and from u versus v graph here, and from 1 upon v versus 1 upon u graph here.